When we're looking at limits at infinity, we're going to start by looking at those limits for polynomial functions. We're going to see that it's a pretty simple activity to find the limit as x approaches positive or negative infinity of a polynomial function. We'll begin by letting p of x be some polynomial function then the limit as x approaches infinity of p of x is equal to the limit as x approaches infinity of a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 and so on. This is our general form of a polynomial function, plus a sub 2x squared plus a sub 1x plus a sub 0. And what we're going to do, because we have an unknown number of terms in this polynomial, is we're going to do an algebraic manipulation of this polynomial that's going to allow us to ignore almost all of the terms. So this is how we set it up. This is equal to the limit as x approaches infinity of x to the n times, we're going to factor x to the n out of every single term in this polynomial. So when we take x to the n out of the first term, we just have a sub n. Then in the second term, we've got a sub n minus 1 times 1 over x, because x to the n minus 1 divided by x to the n would be 1 over x, plus a sub n minus 2 times 1 over x squared, and so on until we get to a sub 2 times 1 over x to the n minus 2 plus a sub 1 times 1 over x to the n minus 1 plus a sub 0 over x to the n. All right. Now we know that limits are distributive through multiplication, so we can move on to the next step where we have the limit as x approaches infinity of x to the n, and we'll multiply that by the limit as x approaches infinity of all the rest of this stuff. And I'm going to simplify it a little bit. We know what it is now. I'm going to cut out a couple terms and have it take up less space. A sub n plus a sub n minus 1 over x plus, and so on until we get to a sub 1 over x to the n minus 1 plus a sub 0 over x to the n. Now in that second limit, I can distribute the limit to every term, and as I get to the second and third and fourth and however many there are after that, I notice that there's a constant coefficient in the numerator. There's an x or an x squared or an x cubed in the denominator, and so each of these limits, as I send x to infinity, each of these limits of all these quotients, all these fractions, are going to go to 0. The top is a constant, the bottom is approaching positive infinity. And as a result, in my next step, I have the limit as x approaches positive infinity of x to the n multiplied by, all the rest of these went to 0, but the limit as x approaches infinity of the constant a sub n is just going to be a sub n. and I can rearrange that a little bit. This a sub n is outside of my limit, but I can put it back in, and I can write my limit like this: the limit as x approaches infinity of a sub n x to the n. Well, what do I have here? This limit is actually just of the very first term, the term with the highest degree from the polynomial. So I can make a statement about limits at infinity of polynomial functions. So I'll say this: the limit at plus or minus infinity, because it doesn't work this way anywhere else, you've got to remember that, of a polynomial function is equal to the limit, same, at plus or minus infinity, of its highest degree term. Essentially, the term with the highest degree has such an overwhelming force on the output of the function when x values are very, very large, that it outweighs any effect that any other term might have. Right? Even if the next term only has a degree 1 lower, still the term with the highest degree has the most effect on what's going on in this limit. Or really, it has the only effect on what's going on at these limits as x approaches infinity. So let's look quickly at an example and see how simple this really makes it for us to evaluate limits at infinity for polynomial functions. So here we go. Here's an example. We'll find the limit as x approaches negative infinity of 7x to the fifth minus x cubed minus 100 x squared. And what we're going to do is say, based on what we just saw in the work done above, that the limit as x approaches negative infinity of this whole polynomial is actually equal to the limit as x approaches negative infinity of 7x to the fifth. In terms of what happens when x is decreasing without bound towards negative infinity, nothing else matters in that polynomial except for the 7x to the fifth. So then we think about what happens if we raise a number that's approaching negative infinity to an odd power. That means it would still be approaching negative infinity, and then multiplying by positive 7. Positive times a negative means it would still be approaching negative infinity. So our answer here is that the limit as x approaches negative infinity of 7x to the fifth minus x cubed minus 100x squared is negative infinity.